What are capacitors? Capacitors are electrical components that store electrical energy. A basic capacitor is made of two conducting plates separated by an insulating material called a dielectric. When a voltage is applied across the plate, positive charge builds up on one plate and negative charge builds up on the other. Even though the plates are not touching, the electrical field between them is what stores energy. The current flowing across a capacitor is given by the formula I is equal to C dV by dt, where I is the current, C is a constant term called capacitance, similar to the resistance of a resistor. It basically tells you how much electrical charge a capacitor can store per unit voltage, and dV by dt is the rate at which the voltage is changing with respect to time. So, we realize the current only flows across a capacitor if the voltage it's experiencing is variable with respect to time. We can then deduce that when the voltage is constant, dV by dt is 0 and so I is equal to 0, hence the capacitor behaves as an open circuit. This makes it clear that capacitors are simply devices used to store energy where if connected to a voltage source, they will charge from that source, and then when fully charged, they will open the circuit and essentially behave as another battery. If you have multiple capacitors in a circuit, evaluating an equivalent capacitance is not very intuitive. Unlike resistors, if we have capacitors connected in series, we do not add them all up. We instead use the formula 1 over C equivalent is equal to 1 over C1 plus 1 over C2, etc. Similar to evaluating resistors in parallel. And using the same reverse logic, we add them all up if they are connected in parallel. The power across a capacitor can be evaluated by using the formula P is equal to VC IC, where VC is the voltage across the capacitor and IC is the current across it. And the energy is equal to half CVC squared.
So in this exercise, we have a voltage source in series with a capacitor, and we know that the voltage across the voltage source is 12 into 1 minus e to the minus t, and the capacitance of the capacitor is 20 microfarad. So in the first question, we are asked to find the current flowing through the capacitor. So since the capacitor is connected directly with the voltage source, so the voltages across them is going to be the same. So we can use the formula that I is equal to C dVs by dt. So we will need to find V dVs by dt first. So we have that Vs is equal to 12 into 1 minus e to the minus, 10t. Now we derive it with respect to time. So we leave the 12 outside and we derive what's inside. Derivative of 1 is 0. And for e to the minus 10t, it's just e to the minus 10t. And we multiply by the derivative of minus 10t, which is minus 10. And so the derivative will be equal to 10e minus 10t, which is 120 e to the minus 10t. Now, to find I, we just need to multiply this quantity by the capacitance. So the capacitance is 20 microfarad, so it is 20 times 10 to the negative 6 farad times 120 e to the minus 10t, which is equal to 2.4 times 10 to the minus 3 e to the minus 10t amperes. Now for question 2, we are asked to find the power and the energy stored in the capacitor as a function of time. So for the power, we know that the formula is V times I, where we know that Vs is this and Is is this, so we will just multiply them out. So we'll get 12, 1 minus e to the minus 10t, times 2.4 times 10 to the minus 3 e to the minus 10t. And this is the expression for the power in watts. And finally, for the energy, the equation is half C Vs squared. So we plug in half. C, we know it's 20 microfarad, so 20 times 10 to the minus 6. And Vs is this expression here, and it's all squared. And the unit is joules. Now for the final question, we need to find the power at 2 milliseconds and the energy at 2 milliseconds. So it's a very simple question. We just plug in, instead of time, 2 milliseconds, which is 2 times 10 to the negative 3. Also, a proof to what we discussed earlier about the capacitor acting as an open circuit when it is fully charged, we can see that as t tends to infinity, so when the capacitor is fully charged, I will actually be equal to 0.
Why capacitors? Where do we see capacitors in the real world and why do we use them? Actually, capacitors are one of the most important key components found in almost every electrical supply we use daily. One of the most common applications is in power supplies and chargers. When you plug in a device, the voltage coming from the wall is not perfectly constant. Capacitors help smooth the signal by storing energy when the voltage is high and releasing it when it drops. This makes the output much more stable and safe for sensitive electronics. We also see capacitors in camera flashes, where they play a very different role. Instead of smoothing energy, they store it slowly over time and then release it almost instantly. This sudden discharge produces the bright flash of light we see in cameras. Capacitors are also widely used in audio systems, where they help filter signals. They can block unwanted low frequency noise while allowing the useful part of the signal to pass through, improving sound clarity in speakers, microphones, and communication devices.